Section 6.1, Slope Fields and Euler's Method. As a review, differential equations are any equations where we have variables and derivatives, okay? And there can be multiple derivatives, but oftentimes, at least in this class, we'll most often just see one. Now, as a reminder, any solution is an equation where the derivatives will satisfy whatever that differential equation may be. So obviously when we solve them, we'll do a lot of integration. However, there are times when dealing with these sort of things and when they're not as simplistic maybe as this one, it may be difficult to solve them. To deal with that, we have something called slope fields. Now, again, you've seen this before, but as a reminder, slope fields are just graphs of these short line segments that basically give you that instantaneous value of the slope, right? The value of the derivative at any given point. And what it does then, when you kind of do that for many different points, is give you a big general shape of what all the solution curves look like to help you learn about the solutions. Now, again, because not all differential equations are even solvable, this gives us a chance to have an understanding of what those solutions generally could look like. So as an example, we have, y prime equals x. This just means, of course, that, in this slope field, the slope at any given point, that, derivative is always equal to the x value. So that means every single column is going to be the same. And when you draw it out, at every little dot, it ends up looking like this. And again, as you can see, all the columns are the same because when x is 1 or 2 or 0, that is the slope. And then clearly you can kind of get a sense of what that solution curve looks like. In this case, probably a parabolic sort of quadratic, right? Because obviously we have x to the first. As a different sort of example, again, what if you had the derivative equals like the sum of x and y? So here, when you look at each ordered pair in the region, you have to add them together to give you that instantaneous rate of change. And again, in doing so, you'll visualize what the solution to a differential equation like this would be. And obviously one like this would not be as easy to see as maybe an obvious one like this, because that's just x. It's kind of an easy antiderivative. This is a little bit different. And again, if you plug in all the ordered pairs and literally add the x and y's together and kind of give yourself those little line segments, the solution ends up looking like this. And clearly you can kind of see a different shape depending on where you go through and things like that. Now, when we actually want to use slope fields, a lot of times we might use them to make what's called a solution curve sketch. And that just means that, we're going to go ahead and make the slope field, but more importantly, we have a certain place where we care about, what the solution may look like. So in this example here, we're going to sketch the slope field for the derivative equal to 2x plus y, and then we want to go ahead and sketch what the solution curve would look like passing through 1, 1. So we get an idea, given that condition, of course, what the solution would look like. Okay, so to begin, we want to go ahead and plot these dots. We want to go ahead and make sure we get those spots taken care of. So of course, to do that, we're basically going to double the x and add the y at every single one of these points. So if we go ahead and start with the origin, obviously that's where x and y are both 0. So 2 times 0 plus 0 is 0. So put a nice horizontal line there. And then what I do is I try to find other places maybe we get 0. Now clearly if I go to -1 for the x and then go up 2 for y, that's going to give me again a 0 because you'll end up with -2 plus 2. So that's another easy spot. Likewise, if I go over 1 for the x and down 2 for the y, this gives us a -2 for y and a +2 for x. So again, a nice easy one. When I draw slope fields, I try to get the 0 ones first. They're just the easiest ones to deal with. Now, obviously, for the rest of these, we're going to be looking at just plugging ordered pairs in. So, for example, if I just go up here to 0, 1, that means it's just going to be the y value, 1, because 0 plus 1. So we have a slope that looks like, up 1 over 1. And then, of course, here get a slope of 2. So just make it a little bit steeper when you draw it. Okay, and again, we're not looking for absolute exact precision, but what matters is that when you go from, one spot to the next, you get the sense of how the graphs will be changing. This slope obviously being, not as steep as maybe this slope. So let's go ahead and just fill the rest in. And again, by doing so, you just plug the ordered pair in to calculate the value. Now that I've filled the rest, you can kind of see some patterns, okay? And I will admit some of my sketches real quick over here almost appear vertical, but because these are such smaller numbers, I just want, you have to kind of have a steeper slope here. Because obviously over here at, -2, this is basically -4 plus -1. This is a little bit -5. So clearly it's going to be pretty, steep in that area. So I will admit my sketch is a little off because I almost made them vertical, but really the idea is it just gets steeper in a negative way as we kind of move down from the graph. Now, what we want to do, of course, is sketch the solution curve. So the first thing is we want to know that we're going through 1, 1. So we're going to go ahead and make a dot here at 1, 1, just to make sure we know kind of where we're going through. And then just to visualize what that slope is, we're going to move left or right of the dot, kind of flowing with the way the little line segments tell us. So obviously going up this way, it's kind of showing we're floating up this direction. And then kind of going the other way, it kind of sort of levels outish kind of down here, and then clearly is going to have a direction kind of moving up this way. So it may not be perfect, but at least gives us a sketch, an idea of what the solution curve in this region would look like. Now, clearly, if I had chosen a different point, we would get a different looking graph, right? Because these slopes are kind of doing different things, different places. But going through the order pair 1, 1 and kind of flowing left and right of it, following where those line segments take us, give us this picture. And this would be our solution curve. Now let's try doing some matching just to practice knowing what we're looking for. So as you can see here, we're given a couple slope fields. What we want to do is match for each slope field the equation, given these options, that could be the general solution it represents. So in this case, again, given the slope field, we want to look at the shape it creates. So we can figure out what general solution would that kind of be looking like. So what I like to do sometimes is kind of just flow along with my pen or pencil and see that shape. In this one, I definitely see it kind of going down and then up and then down and then up. Definitely getting a trig feel to it, sine or cosine. Now, obviously, sine and cosine are both options, but to really know which one's which, I like to really think about what it looks like around the origin. Around the origin, I have a slope of 1. So clearly, I'm kind of moving up at, coming out of where, x is equal to 0. So that leads me to feel like this is more of a sine graph. Remember, cosine kind of peaks right around 0, where sine is kind of coming out of the origin, right? So I feel like on this one, the safe choice would be f. So in this case, that looks like the sine graph. Now in the next one, we definitely have vertical over here, and as we move left to right, it kind of levels out, but then it gets, it gets real steep, almost vertical again over here. So you kind of get this sense of flowing like this, and clearly that really does feel like a like a cubic function, okay? So looking at all my options down here, it looks like option D is the only one that's actually kind of cubic. So I think that would be the best choice. Now let's go the other way. Here, we're given 6 different slope fields, and this time, instead of looking at the pictures themselves and trying to identify what it's trying to describe as far as the general solution, this time, as you can see, given our options, we're going to try and match which ones would be created by which of these derivatives, okay? So which one would kind of, as far as the differential equation, create each one of these slope fields. Now, sometimes, especially with this many options, it can be a little bit difficult to see what's going on, and I always like to focus on zeros, okay? Those are really nice places when you start and you're trying to narrow it down to what's going on with it, as well as also sometimes a general shape. So first off on this one, on my first graph, whenever y is equal to 2, we're getting a 0. So if I go down here and I'm looking for something that would make that happen, clearly number 3 kind of jumps out at me as saying, well, if anytime y is 2, clearly 2 minus 2 is 0. So I think the first thing I'm going to put here is definitely differential equation number 3. Now in my next one, we kind of have a curve this way, but again, what I notice is anytime x is 0, the derivative, right, the value of the differential equation is also going to be 0. So I'm going to go down here and look for something that is going to give me a 0 value anytime x is equal to 0. Well, this one sort of feels like that, right? Because obviously the sign of 0 is 0. And so does this one, because again, we have this here. Also, 2 is another option where if x is 0. However, what I noticed though is at the origin, we do actually have a slope there, which means y can be 0. So it couldn't be this one. And kind of looking at the shape, I don't think we're plugging values into sine, because obviously when you evaluate sine, you get more of a trig kind of curve, a sinusoidal curve. So I don't think it's that one. So I think it's this one, okay? Because we also looking at the solution almost kind of looks like a quadratic. So having a linear derivative kind of makes sense as well. So I think this one is going to be 4, where it's just basically the derivative equals x. Now in this one, the one thing that jumps out at me is there's no slope values right here along the x-axis, or when y is equal to 0. So I think what really jumps out at me is this would be number 2, because clearly y can never be 0. It gives you an undefined, non-existent slope. So in this case, I think it's clearly going to be differential equation number 2. Now in this one, again, what jumps out at me is not only is like our second one, anytime x is 0, we get 0, but also I get this kind of trig flow, right, like a sine or cosine graph. So I think definitely this is going to be number 6. Because not only does x make it 0, but you get that sine feel cosine field kind of thing. So I definitely think this is coming from that. So we're going to call this one number 6. And then in our next one, again, what I think is interesting is whenever x and y here, like along this line, that's when we equal 0. So basically, whenever x and y are the same thing, which is definitely what's going along on this line, we equal 0. And that really jumps at me down here because we have x minus y. So when those are the same, it gives me the 0 slopes. So I'm going to say that's going to be differential equation 5. So then by process of elimination, this one over here should be 1, and then if I double check that, obviously differential equation number 1 is simply e to the x, and clearly this looks like an exponential, which makes sense. Okay, now before we move on from slope fields, let's also go back to what type of questions and things are going to ask us on an AP question. So I'm going to run through a quick AP free response example to remind us what we have to do when we're looking for and dealing with these sort of things. Now, the one thing I do want to point out, however, is oftentimes on the AP exam, they may not give you this many dots to deal with, okay? So I do want to point out that's going to be one sort of different thing. But in general, you are going to have to sketch, okay? So for option 1, sketch, okay? And usually when they grade these, what they're going to be focusing on typically are where the 0 slopes are, and then making sure that all the rest of them have the right shape. So it's usually a 1 or 2 point thing focusing on the 0 slopes, because those obviously have to be little horizontal segments, but obviously the rest of them just having the general shape that they're looking for. Now in our differential equation, because it's xy on the top divided by 2, this fraction will equal 0 whenever x or y is equal to 0. So that means on the x and y axis, I can go ahead and just make horizontal lines for all of those, and those are easy, nice and quick ones I can sketch in. And then of course the rest of them we'll just plug it in. So for every ordered pair, we'll multiply the numbers together and divide by 2. Okay, so now as you can see, I definitely have this taken care of for step number 1. And again, what we're going to focus on is make sure you got the 0 slopes where they need to be, but also make sure the other ones have the general shape that they need to. So in this case, kind of moving up this way, and then kind of moving down in that direction. Now for part B, what it wants us to do is basically say, let's let some function f be a function that satisfies the given differential equation. So that could be some kind of solution. What we want to do is find the equation for the tangent line to the curve, right, whatever this may be at f, through the point 1, 1. And then once we have that tangent line, obviously we're going to use it to approximate what the value of f of 1.2 is. So obviously, since this is our base point, we go shifting over a little bit. It won't be a perfect approximation to the curve, but obviously the tangent line being relatively close to it should be decent. So obviously, if we want to write the equation of a tangent line, the two things we need are an ordered pair, which we already have. We have the ordered pair 1, 1, but also the value of the derivative. So what I need is, what is the value of our derivative at the ordered pair 1, 1? So if we plug in 1, 1 into the derivative here, which is basically x times y divided by 2, it's going to give me a slope of 1/2. So now that I have my slope and my point, we can create that. I'm going to use point slope form. We're going to create our tangent line. So it'll be y minus the y value equals our slope times x minus the x value. Now our second piece obviously is to use this equation to figure out what the value of the function would be, or y value, when x is 1.2. So that means I can just use my tangent line and just plug a 1.2 in here. Now I know it's a decimal, but we're going to do this out of the calculator. So 1.2 minus 1 is simply 0.2. 0.2 divided by, cut in half is 0.1. If I add 1 to it, that's going to tell me that the y value, or the function value here, is going to be 1.1. Now for part C, we want to kind of look back at our estimate here and figure out how does that compare to what the actual value is. Now again, we don't actually know the actual value of the function 1.2 since all we have is the derivative, but what we do know about the graph, in the region around 1, 1 can help us explain that. So basically what we can look at is, if we look up here in the graph, at 1, 1, clearly as we're kind of moving left to right, we can see the slopes are going from negative to 0 to positive to steeper, I guess more positive. So clearly around 1, 1, we can see that the slopes are increasing. Now what you want to take away from that is, if the slopes are increasing, that technically means the derivative is increasing. And by definition, when the first derivative is increasing, that means the second derivative is positive. So around 1, 1, we know the second derivative is positive, which tells us we're concave up. Now what we want to take away from that is this. If we're concave up, right? So the graph opens up this way. And at that point, we make a tangent line. That means that for any little approximation we do, right, just a little bit away from 1, 1, in this case 1.2, we're going to be below the curve, because if we're concave up, that means we know the curve is opening this way. Any tangent line we draw will have all values either right at the point or just below it. So the real actual value is going to be a little bit higher up than what my tangent line tells me. So my conclusion here is that as far as my approximation, right? So in this case, the 1.1 that I came up with, right? That is going to be a little less than the actual value of 1.2. And again, my justification is that f is concave up, at that order pair 1, 1. And again, because of that, that means that the tangent line will always be below the curve. So any values the tangent line gives me will be a little less than what the actual value of the function is going to be. Now, the one new part from this section that we didn't see last year is something called Euler's method. Now, Euler's method is this method obviously named after the mathematician Euler that gives us a numerical approach to approximate a particular solution, right, of a differential equation. Now, obviously, we just did it a moment ago in the AP question using a tangent line. This gives us something that's a little bit better than using a tangent line. And the reason for that is, a tangent line remains linear the entire time. Okay, so looking at our like the previous example, the further away from x you get, obviously, the worse the approximation may be. And again, it just remains linear. Euler's method helps us kind of take the idea of a tangent line and use multiple to get closer, right, to what that approximation may be. It gives us a method. And we can choose how close we want that approximation to be. The number of times we kind of use this approach and how big or small of jumps we make, we can actually get much better approximations than a tangent line would give us. So the way it looks is this. Suppose we have this curve here in gray. So we've chosen this point, I'll just call it x sub 0 on the curve, and we initially drew this tangent line. Now again, clearly if I use this tangent line to approximate a value, it gets further and further away from it. It doesn't become as very good, right? However, with Euler's method, we go a certain distance away, and then after we hit that certain distance, we update it, and we change where that tangent line really is and kind of go a different direction. And then again, after going that certain little distance, change it. So by altering and using multiple tangent lines, as you can see, the approximates better follow curves, which again, just gives us better approximations when we're using those. So the way we're going to label this and look at it, obviously, is when you look at this, we are going to begin at some, x sub 0, and then we're going to pick a certain distance, okay? So this right here, we'll just call this delta x. We're going to know kind of how far apart we're going to go here, and that distance gives us our next value. We'll call that x sub 1. Now, once we figure out how far over to go, then we got to figure out how far up and down this is, right? So this is going to be our delta y. Now, in order to figure out what this delta y is, we're going to have to punch up some numbers, okay? But we're going to figure that out, and then that gives us basically our new spot, okay? So we have this updated idea. Now, as we do this, we're going to be doing it with numbers, okay? So I know I'm kind of generically talking about it with x and y's, but Euler's method is all about evaluating function values, just like we did in that last AP example. So when we do these things, we're going to update, and when we do this delta y, we can literally combine that with where we started at to help us understand where this is going to be, right? How is the y changing? And that, as we do this over and over again, and can give us a much, again, better approximation to a tangent line. So let's come up with how this actually works. So first off, we're going to have our delta x, right? We're going to have that kind of decided, right? We'll kind of know how big of a jump we're going to make. And then when we do that, obviously, we're going to figure out our next point, okay? So that means when we talk about initial point, we're going to call that our x sub 0 and our y sub 0. And that's going to be information that's going to be given to us. We're going to know where we're starting. And then our step, obviously, is going to be that delta x. So when we talk about that right there, as far as, calculating the step and everything else like that, we're just going to refer to it by that number. And we're going to know what it is because it'll basically be the difference between where we're starting and the number we want to, figure out, right? How big of a jump is going to be from one to the other based on, what we're doing. Now, to calculate that, obviously, it kind of depends on how many of these little things we're going to do, right? So when we make the calculation, it's going to be very similar to when we did like right and left and trapezoidal and things. We're going to take basically how far we're going, right? So how much distance it is between basically the actual approximation we want, and that'll be and our initial point. So that's going to be kind of our b minus a, and then we'll divide that by how many steps we're going to take. Okay, so in this case, when we talk about step, it really is the idea that as we do this, we're kind of breaking up how far we need to go and obviously how many steps we feel like taking. Now, obviously, the more steps we take and the smaller this kind of jumpy column is, the better it can approximate the curve. But that does require a lot of work. And maybe the approximation doesn't need to be super, super, super close. So maybe 2 or 3 steps might be fine. But again, that will actually be given to you. So the A and the B is going to be from initial point to your goal. And the N will be the number of steps that they're going to ask you for. So that's how you figure out the step. Now, the last thing, of course, is to figure out, well, how to figure out that change in y. Well, as a reminder, right, when we talk about the change in y over the change in x, that's basically looking at the derivative, right? Because obviously, when we make tangent lines, the slopes of these lines is the derivative. So what we're going to do is basically solve for this. So that means multiply the delta x to the other side. So that means we want to calculate delta y. All we're going to do is basically take our slope, which by the way is the derivative, and multiply that times our delta x, which again we calculate as far as our step. So that's kind of the general idea. And then again, every single time we come up with our change in y, we just kind of add that on, right? We figure out where that takes me for my initial y, and that updates the approximation. Okay, so again, we're going to know how many times we're going to do this. We know where we start and end, and every time we go through this process, we get a little bit better and really have the y value zone in on where we're going. Now, we're going to use a kind of a little table, and I should say I'm going to use a table here, and I hope you do too, to kind of organize your work and make sure you get all the right pieces in the right place. And then once you know how many steps you're going to take, you can kind of follow that table along to make that work. So let's write down in general all the pieces now here step by step. So we're going to approximate the values of a particular solution, okay? That's obviously the goal of this thing. So step number 1, determine the number of equal steps. So like I said before, we're going to take b minus a and divide the whole thing by n, okay? So this is going to be our delta x. Now, when we do this, obviously you want to remember that our a value, that's going to be that initial x. Now, the b value, right, this is going to be the value that we're trying to approximate in the function. So you're going to look at, well, what are we trying to plug in? What are we trying to figure out? So this is the value to approximate, in the particular solution. So the a will be, given to you as the number there, and then you're going to have to look at, well, what are we trying to figure out? Okay, and that's going to tell you where the x is n. Okay, that's your b value. And then, of course, and this will be given to you, n is going to be the number of steps. Okay, so normally, you could kind of do this on your own. Say, I want to do 5 or 6 steps. But for the purposes of doing this in class, we'll tell you, take 2 or 3 steps. But clearly, the more steps you take, the better the approximation. Because clearly, the more steps you take, the smaller each increment it is, and the curve better is approximated by, this method. But we also don't want you to spend forever on it. So again, we'll probably tell you 2 or 3 steps. Now, once we figure that out and we have that initial point, let's calculate slope. Well, obviously, that's going to be the value of the derivative, right? And then we're going to evaluate that at our x and y. So we'll go ahead and plug that in. And that's going to give us our slope at any given spot. So don't forget, when we look for that part of it, that's going to be the thing. All right, so we'll just say that's our slope. Now, to calculate our change in y, which is a big deal, because once we figure out how y changes, that's going to help us update, right, our y to figure out what the approximate value is. All we have to do basically is, like before, we're solving the kind of the slope formula, for delta y. So that means what we're going to do is take our slope, right, the number we calculated, the value of the derivative, and just multiply that times delta x. Because again, the change in y over change in x is equal to slope. So by solving for rise, which is really what we're doing, you just take run times your slope. Now, the most important part, of course, is calculating the new y. So we're going to take our y value that we're at. So the first time it'll be y sub 0, and then it'll be y1 and y2 and so on. Whatever y value we're at, we're going to go ahead and add on that change in y that we just calculated. Okay, and that helps us update what value we're at. And again, as we keep doing this, this updated y value becomes closer and closer to give us that approximate. Now, if we only do it 2 or 3 times, and we only update it a couple times, that's going to be fine. But again, the more steps we do and the more times we refine our answers and get closer and closer and closer to it, the better the approximation is going to be. So that's why I say repeat, because the number of steps is going to tell you how many times you kind of go through this. So in a minute, when you see this example, you're going to see me kind of organize all my work in a table just to make sure I'm getting all the right pieces and the right steps, and you can again see things as they evolve to becoming the solution. So in our first example, as you can see here, we're going to go ahead and, given this differential equation, and the fact that, of course, we have kind of our spot, we want to approximate this value, okay? So I'm going to kind of start at the point 0, 5, but I want to know, approximately what the value of the function is at 0.8. So we're going to use Euler's method, and for this first example, we'll just do it with 2 equal steps. So the first thing we got to calculate, of course, is, identifying our pieces, right? What's our A, what's our B, and what's our N? Because we can't do anything until we understand that. So looking at our information, the x value we're starting at, because again, a and b are x values, is 0. Okay, so that means our a value is going to be 0. And then looking at what we're trying to plug into the function, as far as x value, is 0.8. So we're starting at 0. We want to get to, plugging in 0.8. So that's going to be my b. Now, again, the problem said, go ahead and use 2 equal steps to make a nice, easy example. So our n is going to be 2. So the first thing I got to figure out then is, what is my delta x? Okay, so that means I'll take our b minus a over n. So really it's just 0.8 divided by 2, so we get 0.4. All right, so I'm going to use the table, and our goal is to figure out, when I plug in 0.8, approximately what should that be? Now remember, like a slope field, we assume right now we're kind of put ourselves in the situation that we couldn't have solved the differential equation, and we just want to get a quick approximation. Okay, so I know the value at 0, trying to approximate the value at 0.8, and so our final result is going to go right here. So to begin, we're going to fill in this little table here. Okay, so every line is kind of like doing a step. So to begin, the very first line, we're using obviously our x sub 0, y sub 0. So in this case, the order pair 0, 5 is where we're starting. So our initials x is 0, and we know the y value there is 5. Now clearly, when I plug in 0.8, it's not 5, but this is the number we're going to slowly get updating closer and closer to figure out the approximation. So the second step is figure out the slope. Okay, well, as you can see from the derivative, you take the x value minus 2. Well, 0 minus 2 tells me that this is going to be negative 2 at that point. Now, again, to figure out what my delta y is, we're going to take our slope, right, the number we just did, and multiply that times how big of a step we're taking, our delta x. So that means we're going to take our negative 2 times 0.4. Okay, we take our slope times our delta x, and that will happen every time in this step. So if I take negative 2 times 0.4, that's going to give me negative 0.8. Now, I've calculated, once I move over a little bit using this slope, how much the y changes, right? This is my delta y. So remember, the y started at 5, and the change in y needs to be negative 0.8. So if I take 5 and add on that negative 0.8, that tells me that when I update just a little bit, when I make that little delta x movement, the y value becomes 4.2. So that's kind of one step through it. So again, we know at 0 the y value is 5, but going through this process one time, right, basically using the tangent line, we're getting closer and closer to the new approximate, which we believe to be 4.2. But obviously we're going to do this again, okay, because we know we have 2 steps planned, so we're not there yet. So that means we have to just go to our next point, okay? So again, we started at 0. When we get to our next point, we're jumping up by delta x. Okay, so if our first point started at 0, the next point that we're going to adjust at is going to be 0.4 more than that. So that means 0 plus 0.4 gives me my next x value. Okay, so again, just add your delta x. Now, we already know the new y value because that was the purpose here. We know we're at 4.2. So we can go ahead and copy the number over there, 4.2. Okay, and again, when you think about it, we started at 0, jump up by delta x. We started at 5. Jump up by delta y. Or in this case, I guess down because it's negative, but using delta x and delta y, that's how we get these numbers. So now that we have these numbers, let's do the process again. Plug these numbers into the derivative, right, to get our slope. Well, again, the derivative is the x value minus 2, right? So we take 0.4, take away 2, so that's going to give us negative 1.6. And then to get our change in y, we're going to take this, negative 1.6 times our delta x, which again remains 0.4. So when I take my negative 1.6 times my 0.4, that's going to give me my negative 0.64. So when we look at our updated y, as always, let's take it where we were. We were at 4.2. Now we're going to add on the negative 0.64. Okay, so our y value where we're at 4.2, when we do the change in y, our negative 0.64, and put those together, that's going to give me a y value now of 3.56. Now, it should make sense to you that as we're looking from step to step, that from 5 to 4.2 to 3.56, the y values are getting smaller, but again, that makes sense because the slopes are negative, okay? So that should be something that as you're looking should make sense to you. So that, of course, means that this is my new updated y. So when I look at the point I'm at now, my x now is going to be 0.8, because again, the change in x is just increasing 0.4. My new y that I just got was 3.56. Now, we're done because, again, we're only asked to do 2 equal steps. So the first line was our first step, the second line was our next step, and really we started out at 0.5, went to 0.4, 4.2, and then got to 0.8, and then 3.56. Now remember, this number should be the value we're trying to approximate at, because we purposely did this in 2 steps. So we calculated it so the x values we chose got us there in 2 steps. So this number right here should be the one we're plugging in. And clearly, as we updated y twice, that approximately 0.8, the y value is the 3.56. So this right here is the approximation we're looking for. Now, is it good? It might not be too bad, but clearly if I'd done more and more steps, I would get an even better answer.